So, what do you get when you put the Chem Cats together with the Mythbusters? You get the Chembusters.
So what myth are we busting today?
Well, let's have a look.
Myth. Chemistry is boring.
So how are we gonna bust that?
Why, with Lewis structures and a bar of soap, of course.
Soap? Of course, that's genius!
So let's get down to the nitty-gritty. History, please.
Whoa, hold on a minute. What exactly are these Lewis structures you're talking about?
Well, you see, they are kind of like X-rays for
Whoa.
atoms.
How do you mean?
Well, they reveal how the valence electrons and bonds are arranged in relation to other atoms. Kind of like this.
That's cool. So that makes sense now. So who's the genius behind all this?
That, my friend, would be Mr. G.N. Lewis.
I remember this guy. Do you know he was homeschooled until age 14?
Duh. Didn't you know that he also had a PhD from Harvard University under Theodore Richards?
Who's that?
He is the first American to win a Nobel Prize in chemistry.
Interesting. Do you know Lewis also worked with chemist Ernst and Oswald?
Who doesn't? And he also held appointments at MIT and UC Berkeley.
In 1902, Lewis illustrated valence electrons by using his idea of the cubic atom.
So you mean like today's octet rule?
Exactly. 8 corners in a cube, 8 electrons.
Oh, so kind of like this box of soap?
No. More like this, actually.
Oh, it looks like a first grader drew that.
That's the original drawing of the cubic atom that Lewis showed in 1902. See the concentric cubes?
Makes more sense now. In 1916, Lewis published his theory defining a chemical bond as a pair of shared electrons, and that's where our modern-day Lewis structure actually comes from.
And later, in 1923, Lewis redefines acids as electron acceptors and bases as electron donors, explaining the incomplete octets. He sure did touch on all the bases of the X-ray of the atom, didn't he?
You bet he did. And now that we know the history, can we please talk about the bar of soap?
Where do you keep getting all these bars of soap from?
Don't worry about it.
You know what? Never mind. Let's go to the soap.
Thank you.
So what exactly are you wanting to do with the bar of soap?
Well, I was thinking we could bring in our expert, Dr. J.K., who is experienced in all things Chem 107.
I'll go get her.
Hey guys. So, where's the other guy? Where did he go?
I don't know.
Okay.
Welcome to 60 Seconds with Dr. J.K. and the Chembusters. How are you doing today, Dr. J.K.?
I'm doing well. How are you today?
I'm doing fine. Excellent to hear. So, have you ever tried to eat a big, fat, juicy hamburger with grease just dribbling down your cheeks and soaking through your napkins, and then try and wash it off with water in the bathroom and you fail miserably? Well, today we have your answer with soap. So, why does soap and water, and not just water alone, wash away the grease?
That's a very good question, and we can actually examine that by looking at the X-ray or the Lewis structure of the soap molecule. So, as you can see here on the screen, this is what a soap molecule looks like. It actually is composed of 2 parts, a polar head, which helps to tackle the water, and a nonpolar tail, which helps to tackle the grease. So this tail is made up of hydrocarbons, so hydrogens and carbons bonded together, and that's where the Lewis structures actually come in. So let's examine that in a little bit of detail. Why is that tail nonpolar? The reason for that is because, first of all, there's only a small electronegativity difference between the hydrogens and carbons, and second of all, because of the tetrahedral arrangement around the carbons in that tail, which cancel out any kind of small dipole moments. So what is a tetrahedral arrangement? If you continue your studies of Lewis structures, you'll actually get into a study of VSEPR theory, which helps you to determine the 3-dimensional structure of the actual molecule based on your bonded and non-bonded electron pairs. So, looking at carbon.
Oh, I got you on this one. Right. So, carbon has 1, 2, 3, 4 valence electrons, correct?
Yes, it does.
Excellent.
So, that's correct. So, you want to look at the valence electrons on carbon, and if you will actually look here, because the carbons in the hydrocarbon chain have 4 bonded electron pairs, that gives it a tetrahedral molecular shape. So, what the tetrahedral molecular geometry means is that the hydrocarbons in this chain actually look like jacks, kind of like this up here.
Oh, so what you're saying is that this tetrahedral arrangement of the hydrogen atoms around the carbon atom cancels out the individual dipole moments, giving you a nonpolar tail?
Yes, that's right. So because of this tetrahedral arrangement of the hydrogens around the carbon, there's a certain symmetry that cancels out any kind of movement that would make it polar, which is why this tail is nonpolar. And therefore, you need soap and water with its dual nature to be able to tackle that grease right off of your fingers. Yep.
So, welcome back to 60 Seconds with Dr. JK and the Chembusters. Today we're going to discuss ozone. And as has been in the news lately about carcinogen and other cancer-causing agents, UV light is harmful to my beautiful skin. And so, as some of you may already know, ozone, or O3, absorbs some of these harmful rays from the sun. And so, how do Lewis structures exactly show ozone's superhero ability to save the atmosphere, Dr. JK?
All right, so let's dive right in. So before we actually get into the explanation of how Lewis structures work in action, we've got to examine the structures of O3, or ozone, and O2, both of which are in our atmosphere. So, looking at this periodic table of elements.
Oh, this again. Okay. Oxygen has 6 valence electrons, right?
Yes, that's right. So because oxygen has 6 valence electrons, the resulting Lewis structure for O3 actually looks like this. So reason why there's an arrow between these two different structures is because O3 is actually a resonance hybrid. So it has two different resonance structures. And just keep in mind that O3 does not switch between these two resonance structures, but instead the actual ozone molecule has an average of these electron bonds that are formed. So because this has a double bond and a single bond, the actual bond length would be somewhere in between, like an average. So let's compare this to the structure of O2.
Here is your marker.
Thank you. So, O2 actually looks more like this. So 6 valence electrons plus 6 valence electrons is 12 valence electrons.
Correct.
So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, 12. So our O2 molecule actually has a double bond. And compared to the resonance hybrid of O3, or ozone, which has that averaged bond between a single bond and a double bond, just this double bond by itself in O2 is stronger. So then photons with their wavelengths actually cannot break through O2 compared to O3. So O3 actually is a bit self-sacrificial. That's how it saves the Earth, as we'll explain in the coming slide. All right, so Lewis structures in action. As you can see in this diagram, we have the ozone molecules in the atmosphere and incoming ultraviolet light here. So what happens when this ultraviolet light comes in contact with the ozone molecules is that the ozone molecules actually break apart because their bonds are weaker into O2 and an oxygen atom. So that breaking apart actually helps to absorb the photon's energy, because the wavelength of the photon is just the right wavelength for that to be absorbed by O3. So afterwards, O3 comes back together from O2 and the oxygen atom so that it can save the day once again.
Wow, who knew ozone was so amazing?
Right? It's just like ozone's Superman saving the Earth from a meteorite incoming. Yes, so that's how Lewis structures work in nature.
Thanks for joining us. So, thanks for being on the show today. I think it was a really good episode.
I think so too. Thanks for having me on the Chembusters today.
No problem. How's Chem 107 going for you?
It's actually going fantastic. You know, that Dr. Blue, she has a good sense of humor.
Guys, I couldn't find Dr. JK.
We found her. We're finished.
Okay.
But don't put yourself up, dude. It's okay. Don't put yourself up. Everybody makes a mistake. It's okay.
Remember, kids, Lewis structures. So, what do we get when we put the Chem Cats together with the Mythbusters? You get the Chembusters.
So what myth are we going to bust today?
Yep. Forgot. In 1916, Lewis published his theory defining a chemical bond as a pair of shared electrons, actually defining our today's modern-day Okay, what do I start off at? Sorry, start over. Hit it again. Hit it. What do I say first?
Things
Whoa, hold on a minute. What exactly are these Lewis structures you talk about?
What?
I forgot.